Good afternoon, everybody. Welcome to the coveted post-lunchtime slot at BlueHat. Are there anybody in the audience that are not already familiar with the good work of David and Sarhan here? Oh, all right, you guys just leave. Come on. So David's been around Windows security space for longer than I've been at Windows. What, Win 7 days and forward?
Something like that.
And he's been instrumental in helping kind of chart that path, that pivot from just defending and reacting all the time to stopping the game of whack-a-mole. It's that role of trying to get us off the treadmill of only being responsive and trying to learn from the things we're responding to and incorporate that new vision of security into upcoming versions of Windows to try to not have to solve the same problems over and over again. Sarhan, basically all things container. If it can fit into a container, or you would like to fit it into a container in the context of Windows, he's your guy, if you want to do it securely.
He's like Yogurt in that respect.
He is. That's actually, you can reach him at yogurt@microsoft.com. That's not true. No. Today's presentation is actually going to be a pretty cool little tour. It's looking at securing the security offered through the Windows Defender Application Guard. And this is one of those efforts that took no small amount of time and resourcing to try to figure out new ways using new architecture inside Windows to provide greater security, greater isolation, greater protection. So consider this sort of a guided tour as to how we manage that pivot and how we evolve Windows. So tomorrow's version is going to be better than today's. Without further ado, David and Sarhan.
All right, thanks everyone. I'm liking this. It has almost like a high school lunchroom kind of vibe here. Someone passed me a milk or a juice or something in here. I like this room. So my name's Dave Weston. Amongst other things, I am a group manager in Windows, and Windows Defender Application Guard is one of the features that I own. I'm really excited to share this with you today. This talk is not just about the feature set and how people use this, which is normally how I talk about this, and rightfully so. It's more the journey for this audience on how do you secure a brand new technology and what kind of effort goes into that. This is definitely an important moment for me, since this was many months and even years of my life working on this feature to try to bring it up, and I know Sarhan feels the same. So we're excited to share. And the best way that I can get you to think mentally, if you haven't tried the feature, which I recommend you do, we just released it a couple weeks ago with the Fall Creators update of Windows 10, is it's a tiny version of the OS inside of the OS. So rather than securing a feature such as a browser or a notepad or a document reader, you've really got to, from a security assurance, analysis, penetration testing standpoint, there are so many vectors. It's an entire operating system that's sort of shrunk down into a feature. So that's a good way to think about this. The first thing I like to do when I talk about a feature is level set. What were we trying to accomplish here? That's absolutely critical. The strategy of Windows, and if some of you have seen my talks in the past have probably seen this many times, is we want to make it as difficult and costly as possible to compromise a Windows 10 machine. That's super critical. It's a simple sort of statement on the face, but it's absolutely critical. We're constantly looking at the economics and the mechanics of attacks and looking at the place that we can most durably drive pain and cost to attackers. And this feature fits into that strategy and the tactics we use. So we want to make it expensive. We're not saying this is unbreakable or using any of those kind of naive terms in the past, but we're constantly looking at how to make things more expensive. And the tactics we use, I think, are very straightforward, but again, important. Our first gold standard of mitigating an attack is to take the vulnerability off of the battlefield. So we're consistently investing in compiler features and runtime checking that would do things like totally eliminate use after freeze. Obviously a tough problem, but we might use garbage collection to do that. Eliminate integer overflows. We can do that through static analysis or through compiler checks. But if a vulnerability doesn't exist, that opportunity for the attacker is completely gone, and that's our gold standard. The second part of that chain is we want to break exploitation techniques. So if attackers are consistently using things like arbitrary read-write by corrupting a particular length field, we would look and investigate how do we break that. The third piece is if we couldn't eliminate the vulnerability and we couldn't stop the exploitation technique, then we want containment. This exploit maybe is given the attacker arbitrary code execution, but we want to contain the damage there. And that is absolutely a critical part of our security strategy. And the fourth sort of tenet here is if all else fails, limit the opportunity for attack. But what we're going to talk about today is why Application Guard and this micro-virtualization technology that we've built in the latest version of Windows is useful from a containment standpoint. So let's look at essentially what attackers are trying to accomplish. So you can really look at an exploit as a weird machine. You start with a software vulnerability, and you want to manipulate it into a mechanism for executing a payload. You'll start by exploiting a common vulnerability class, whether that's a stack or heap overrun, or some sort of memory corruption in most cases. You'll then turn that into a class-specific exploitation primitive. What do I mean by primitive? Primitive is a capability to now program the machine vis-a-vis a vulnerability. So the most common primitive that we see with attackers nowadays is the ability to read-write memory from across a trust boundary that shouldn't be allowed. Very common mechanism for doing that is maybe you get an action script vulnerability in Flash, you corrupt an array length. Now that array is mapped to the totality of virtual memory for a process, and you can read or write things, you can steal secrets, you can corrupt control flow, all of those great things. But the goal there is to execute a payload. And this is a recursive attack chain. So in a normal case, for example, with a browser exploit, you would start by going on this journey to get initial code execution. And then you would move on to attempt to do that from a secondary surface. So now you need to elevate privileges. Again, you repeat the chain. Find a vulnerability, turn that into a class-specific primitive, execute your payload. So containment is really the last line of defense that we have against executing a payload. And as such, we are constantly looking at mechanisms to retain containment as a method for stopping payload execution. This is essentially how we think of isolation and how it fits into our strategy. So our first and broadest mechanism for containment is what we call the app container. How many of you are familiar with the standard Windows sandbox that we call the app container? All right, a few folks, so I'll get into it. So app container has a few properties. It's a security boundary that operates at the process level. It has capability-based resource access, and that means you need to ask for a capability if you want to use it. You start with absolutely no capabilities in the system, not even the ability to talk to the network. You've got to ask for network and be pretty granular. I want client side, I want server side, I want access to the local network. You have to ask for the documents library or specific applications. So it's a way of implementing principle of least privilege. And we've used this to great effect. This is the standard method of isolation for our UWP, or Universal Windows App Platform. So if you look in the store, the vast majority of those apps are constrained by the app container. Microsoft Edge, being the most familiar UWP, it actually runs in the app container. It has a set of capabilities. So if you open up Process Explorer, your favorite tool, sysinternal something, you can actually see what the capabilities are assigned to that. Office Protected View also uses the app container, again, for containment. So the goal of app container is essentially if an attacker was to achieve an exploitive vulnerability from an application running in the app container, at best they would be able to reuse the capabilities of the app, which hopefully, if the developer has done their job right, would limit the damage. Now, an interesting property that we've started to introduce on top of the app container is the ability to restrict the kernel surface. But it's important to understand, especially for the rest of this talk, that the app container on its own simply restricts user mode primitives. So it denies access to namespaces, to files, to network resources. It actually leaves the totality of the kernel, in most cases, open, specifically the system call surface. So even if you're executing code in an app container, you are restricted from maybe accessing files or identities or other resources, but you can actually freely make calls to this 2,000 system call attack surface. So it leaves a lot of opportunity there. So one of the things we've been doing with app container is continuing to invest in it, continuing to make it smaller. The first iteration of app container was actually designed to be broadly used by applications. And that means, although it was an effective sandbox, it wasn't as tight as it could be if it were tailored to a specific application. Microsoft Edge being our web browser and one of the spaces we're most concerned about from a security perspective, one of the things we've done recently over the last several versions of Windows is we've created a profile that's even smaller than the regular app container that we call the least privileged app container, or the LPAC. And that's actually shrunk the attack surface, that is the vents out of that sandbox, by 90%. So it's become an incredibly effective sandbox, and it's something that we're continuing to invest in. Another thing which I'll talk about in a moment is we have started to refactor Microsoft Edge to use less of that kernel attack surface, less of that Win32k attack surface. We factored it off to use to no longer use an entire section of functionality there called GDI, or the graphics interface. And so that opens up the opportunity to begin to restrict attack surface, which is my next slide. So as software isolation has become more ubiquitous, whether that's the software isolation from third parties like Adobe or Google Chrome, who have restricted token and app container sandboxes, or the UWP surface, attackers have responded. They didn't just give up saying, I'm OK with being constrained within the app container. Instead, they pivoted toward this kernel attack surface, and they settled on a new TTP or tactic of combining a remote code execution vulnerability with a kernel exploit. And as I said before, there's plenty of opportunity there, because in the average case for an app container, you've got 2,000 system calls, many of which were written 20 to 30 years ago as a potential attack surface and a method for finding escapes. And so what you see on this graph over here is the instances of kernel exploits that Microsoft's observed in the wild. The vast majority of these have been tied and used as sandbox escapes. And so you see this almost linear increase around the early 2010s, where sandboxes are becoming ubiquitous. You see a growth in kernel, because now attackers are saying, if I want to continue to attack Office, if I want to attack Chrome, if I want to attack Internet Explorer or Edge, I've got to combine that with a sandbox escape. Now, the other interesting of kernel, just as a quick note, is it's also a target-rich surface. So if you get one of those read-write primitives that I discussed previously, there's a lot of things that you can manipulate from a data standpoint. You can copy credentials, you can turn off policies, you can do all sorts of things. So it's a very tough surface to secure. So one of the challenges or approaches to restricting this kernel attack surface that we've seen as an augmentation to user mode sandboxes is something called kernel filtering. So the concept behind kernel filtering is, wow, so by default, I've got this really large 2,000 plus kernel attack surface. I'd obviously like to shrink that, since that's an event out of the isolation surface. So platforms like Linux have very advanced filtering systems, in particular on Linux, something called seccomp BPF, where you can write essentially expressions to filter the kernel attack surface. So in some cases, we've seen people look at Windows or recommend that for Windows, thinking it's very similar to Linux. Now, one of the reasons Windows has a challenge adopting that is, one, we don't document our kernel interfaces. In fact, that's a big part of our development foundation, is by not documenting those native surfaces, we can change them over time and continue to improve them. The basis or the contract or the API that people interact with the kernel is actually a user mode API. So trying to create essentially a clone of this kind of filtering language that exists on Linux on Windows would almost be intractable. In fact, we'd hardly have to refactor a large part of the kernel. So that is sort of an issue with creating that. So instead, what we've done is we've created smaller, less configurable filters for specific surfaces. So I mentioned previously that Win32k and that kernel surface has been rapidly attacked in many cases. And so we've wanted to restrict that surface. And so we've built in what I would call static filters into Win32k. But they aren't quite as flexible as we like, for some of the reasons I described previously. And so in general, although we're really interested in kernel containment, software approaches on their own have some limitations. We're continuing to invest there. But there is essentially a limit to the amount of attack surface you can restrict. So long term, if we're looking at containment, there are other technologies that we should consider in addition to software filtering. So arguably the gold standard when you're talking about kernel isolation or kernel containment is virtualization, right? We bet an entire cloud business, and there are multiple clouds, on the strength of the hypervisor and its ability to deliver multi-tenant security. So it's critical. So we know it's strong. In fact, a little plug here, Microsoft offers up to $250,000 for a Hyper-V escape in our bounty. So that should tell you a little bit about how important we think it is. If in certain implementations on the desktop, two examples I called out here are the Privileged Access Workstation and the Cubes OS, which is on top of Linux, have actually been able to take advantage of virtualization to compose user mode isolation. In the case of the Privileged Access Workstation, concept here is you don't ever compute in the host. You create VMs that are affinitized to scenarios, for example, development scenarios, corporate email scenarios, personal web browsing, and you use that virtualization boundary as a method for containment. So that has obviously a lot of security strengths and is very positive from a security perspective, but I don't know if you'd want to hand grandma or grandpa a privileged access workstation with multiple VMs and say, go to town and do your normal thing. So it's appropriate for high security environments, and it's a place we continue to invest, but it doesn't quite meet the muster of a generalized isolation platform that contains kernel, which is what we're looking for. It's also expensive to configure, and it also is hardware intensive. So looking at the challenges we had either moving to a pure virtualization environment for kernel containment or software filtering, we thought there might be a better way, and that way caused us to look at containers. So as with all things Microsoft, we don't just have one container technology, we have 4. I promise you we need them all, and they're very useful in a bunch of cases. But the meta reason for looking at containers is if you pick the right technology, it offers all of the strengths of a full VM and virtualization with none of the resource hogging and the ability to enlighten it. So I'll quickly run through the different types of containers we have and how we selected it. So the most lightweight container we have, which is awesome from a resource perspective, is what we call a helium container. This is what we use for things like Centennial apps. This offers actually no security value. It's simply file and registry filtering that makes virtualization work here, and is mostly used for abstracting storage and other system resources. So although it's lightweight and attractive from that perspective, obviously it's not going to solve our kernel containment problem. The second container technology we have, which is most closely related to something like a rooted jail on Linux or a Docker-style container, is what we call Argon. And Argon actually spins up an entire separate copy of the user session, and it uses the session boundary. So if you're familiar with multi-user scenarios in Windows, it's something similar to that. So it does provide user mode security, but again, there's a shared kernel there, so it's not going to solve this problem of eliminating the possibility of containment violation through kernel exploits. The second 2 technologies are much closer. They're actually lightweight hypervisor-based virtualization technologies where resource sharing between the host is maximized, so you don't have the full cost of a VM that has to have physically backed memory and is opaque to the operating system. So it's a good balance between resource consumption and security. And so when we look closely at these, we selected Krypton technology as our container approach for Application Guard. So let's talk about what Krypton container technology is and how it affords us some very valuable things. The first most interesting technology from my standpoint, in fact, when I first learned about this, I was totally amazed, is what we call direct map. And what direct map essentially means is, rather than creating a VM with a separate VHD or disk or VMDX if you use VMware, we actually repurpose all of the host binaries to compose essentially a VM image on the fly. So for example, if the child VM needs a copy of kernel 32, it attempts to load it from a virtualized version of the operating system. It talks to its kernel in the guest. That kernel in the guest passed through to the host. The host says, I already have a version of kernel 32, and it maps it into the VM. Because of that, we don't actually need to package up a full operating system in the VM that we use for Application Guard. So for example, Application Guard fully runs Edge, has 20 to 30 services running, can launch Notepad, all of those things. The size of the Application Guard VM is 18 megabytes. That's the only thing that's unique to this VM. The rest of it is completely shared with the host, and that's thanks to Direct Map giving the ability to share both data and image between the guest and the host. And that is really, really an exciting technology that's made this possible. It also keeps down the working set and physical memory requirements of a VM. So it makes it really possible to spin up not just one VM quickly, but multiple VMs in the future. Likewise, there's been a lot of memory enlightenment by the wizards in our hypervisor and base container and kernel teams who have made it possible to use what's called virtual address or VA-backed VMs rather than physically backed VMs. In the old VM technology, you would have to say something like, here's 4 gigabytes of RAM for that VM, and no matter what was happening inside of that virtualized guest, you had 4 gigabytes. In the Krypton world, we now are able to dynamically allocate, collect, and manage virtual address space for a guest VM just like it was another process. In fact, I would go as far as to say that we've created another unit of execution similar to a process or job object, where the NT kernel simply looks at this thing as something it can manage from a QoS or suspension and resource manager perspective. And that's really important, because our goal here eventually is to get kernel containment on every process. So it's absolutely critical that we did this plumbing and enlightenment work to make that as lightweight as possible. And the final exciting technology that you can see in the latest versions of Windows Insider Preview is what we call the integrated scheduler. What that means is that the guest itself thinks it's talking to its own kernel, but it's actually talking to software-implemented virtual CPUs that then pass through to the host scheduler. So that's really cool, because it means that processes running in the VMs, threads running in the VMs, they can be suspended. If you're not using the VM, it can be backgrounded. So that's going to save on battery life, on resource consumption on CPU, which generates heat and battery drain and all that great stuff. So the VM to the host kernel eventually just looks like another process, and it can be managed that way. And so there's a lot of technical jargon that's thrown there, but the net is essentially VMs at the Windows level now look a lot like processes. And that's incredible, because that sets us up to build applications that are essentially based on VMs as a primary containment technology. So where we stand today is we have two containment technology, one that is used for hardware, and today is mostly used by enterprise users, and another awesome sandbox that has both software kernel isolation as well as user mode isolation in Edge. And those are actually combined when you turn on Application Guard. So there's a lot of jokes about dual AVs and those other things, but when you're actually running Edge and Application Guard, you have both the LPAC container and the hypervisor Krypton boundary to contend with, and that actually gives a lot of containment properties. So with that said, actually the first thing I wanted to show you before I pass it on to Sarahan to talk to you about how we secure this thing is what it looks like in action to actually stop an exploit. So what I'm going to show you is an exploit constructed by the Windows Red team, the Offensive Security Research team. And it's actually going to be a browser exploit combined with a Win32k exploit. This is the kind of thing that we would normally do as part of an assessment. Of course, all the vulnerabilities are fixed here. And I can tell you Edge is no different. My team has also exploited Chrome and other browsers here. So this is what we do, is we look at browsers and we try to increase the security of it. So there's actually an interesting point here, and you'll be able to see what it looks like to run a zero-day in Application Guard. So what we're actually doing here is we're just going to start up a native version of Edge, and we're going to point it at a zero-day exploit that combines an exploit in the JavaScript engine with the Win32k exploit. And what you can see here is we actually popped a CMD window there at system because we got full privilege. We broke in containment at the kernel level. So we run that same exploit now in Application Guard, and this is sort of sped up just for speed. You can see it's Application Guard by the orange bindings there, or orange sort of chrome. We run the exact same exploit. When we say, who am I? Again, we're still at system. But this time when we try to write to the host operating system, we're fully contained. And you can see that's possible, and that we're actually running in the container environment because all of the users are fake. So what you saw there was pretty quick and move fast, but that's what exploits do. But the key point here is in both cases, we combined an exploit on the open market that would cost hundreds of thousands of dollars, 2 0 days. One, which is fully contained in the container environment, is still backed by yet another boundary that would have been difficult, and the other one is native. And I think this is a good example of the potential of this technology, and something that we think will make it much more difficult over time to exploit Windows machines. And with that, I'm going to hand it off to Sarahan to talk to you about our security assurance work.
All right. So the strategy we took for securing something that is actually itself a security feature is different from the way we tackle normal workloads from the security assurance perspective. We took on, both us as the OS security team and the Red team worked together with the developers of Windows Defender Application Guard in sort of what we like to call a co-engineering mode, where even at the very core start of the project, the security teams were there to advise on both the design aspects and also kind of the implementation or the choices they made to create, for example, the boundary, the changes in the security boundary from a traditional Hyper-V container. We moved on from that to a full code review of all the check-ins into places where there is a security risk for Application Guard. And of course, beyond that, we have developed a bunch of fuzzers that will continue to run and target the application guard as we develop it and enhance it over the releases. And finally, once we've gotten to that, and once we've arrived at Windows Fall Creators Update, we can now actually give it out to anyone to test out themselves, but also have our red team do a full stack exploit to ensure that the strategies we've taken are sound, and to make sure that we have the design that we wanted in the first place, or if not, to make changes to improve the security of Defender Application Guard before we ship. Now, enough strategy talk. Let's talk about what we actually did, and let me give you guys a cool story or three, or maybe four. So we're going to start with the basically piecemealing the threat model of Windows Defender Application Guard into four separate functionality parts that were all needed to get what you see today, which is an orange or brownish colored version of Windows Edge or Microsoft Edge on your screen. So let's start with storage, because I think David talked about direct map a lot, and he's clearly a fan of this feature, but let's talk about how that actually works from a functionality standpoint. Now, how many of you guys are familiar with Hyper-V containers, or Windows Server containers with Hyper-V isolation, I think is the new name? Cool, actually more than I expected. Now, this model here is very similar to the architecture for Hyper-V containers. We have a read-only share that's passed over VM bus to the guest VM, the Hyper-V container, and that contains the base OS image, the one that it will use to launch Windows itself, and then of course the application you want, in this case Edge. And then second, we have a VHD that's mounted as well. That is a per instance VHD that will be thrown out, that's simply used to capture any kind of writes that the guest needs to do to its file system. And we kind of fake it inside the guest that these two separate volumes are actually a single one inside. It's just the C drive. And any writes that you do are copy on write straight to the VHD. And when we restart the VM, that scratched VHD is deleted, and no persistence of data is allowed, which is great from a security perspective. Now, the interesting thing for Barcelona was, Windows Defender Application Guard was
we like code names.
Yeah, we do. Is the actual dynamic part of this diagram. So what does that actually mean? Why is that folder dynamic or green? Well, it turns out that we don't want to create a whole new folder full of Windows, and we don't actually want to share the Windows folder that you currently have on your C drive. There's too much personal information in there, and there's a risk of information disclosure. So instead, we build a new dynamic base OS folder on your C drive that contains, the same folders that you know and expect from Windows, but instead of actually targeting specific files or putting them into that folder, we instead pass in two different types of links. One link we like to call reparse point, which is actually a view of a folder directly into the base OS folder. This allows for any changes that happen dynamically in that folder to be percolated up to the guest VM. And this is a very powerful primitive, as it reduces our recipe book for building a base OS. We can just say, hey, whatever's in the Windows apps folder, I need it inside. And of course, we can also just hard link files directly from the folders themselves, which ensures that nothing gets passed in that we don't want. We explicitly say, I want, for example, run DLL32, I want this, I want that. And any changes on the host side will not be reflected on the guest side. Now, this kind of allows me to segue into my first bug. It turns out we were a little overzealous in using the reparse point primitive, and it turns out we had a lot of files and folders inside the printer spool folder inside System32. Most of these are necessary for print actions to occur in the guest, even for virtualized stuff like XPS and PDF. Unfortunately, it also turns out that this is a temporary storage spot for the spool service to place files that are being printed on the host machine. So we had inadvertently given the guest VM temporary access to confidential information in the file system. And this kind of breaks our contract for Windows Defender Application Guard, which is to maintain zero disclosure of information about any host information, any sensitive documents, et cetera, to the guest. So this one was a pretty easy fix. Of course, we simply decided to hard link that folder instead and alleviated any temporary file risk as these changes no longer go up to the guest. But we didn't stop there. The VSMB attack surface is really important to us. So we built a full generational fuzzer that actually acts as a VSMB client talking to that server. And if it makes actual file system operations against the VSMB share. This was used to target memory corruption vulnerabilities in VSMB and was very successful in finding use after freeze. This allowed us to both secure Windows Defender Application Guard, but of course also Hyper-V containers in the Windows Server perspective. Moving on, let's talk about networking. So one of the fundamental restrictions that we want to put into the Krypton container is the ability to only access the internet, and not the internet, or not the intranet, or any internet assets that the administrator of Defender Application Guard has deemed protected. So we leverage existing functionality in VM switch, which is the networking kernel interface for Hyper-V. And we add WinNat to allow us to use any network adapters currently plugged into your system, so that if you, for example, use Wi-Fi at home, but use a Ethernet connection at work, that does not mean you have to switch virtual network switches or do any sort of fancy work there. It automatically happens in the background. And some of you guys who are avid Hyper-V users know the pain of trying to switch external switches around on your laptop. So we leveraged the VM switches modular plugin system to add a new filter driver that inspects packets coming in from the guest, determines whether or not you were supposed to be, or the Krypton container was allowed to go to those regions, and makes a decision to accept or deny your connection and throw it out before it even goes any further than that. Of course, there are some issues with this. One of the biggest ones is that if we block out a significant chunk of your intranet, then certain functionality like DNS lookups will not work if you are dependent on your local DNS for name resolution. So for this reason, we provided the guest with a new, much more pared down and controllable interface that allows RPC function calls to be passed over VM bus once again to the host. And we host this in a separate user mode process, and it makes the DNS request on the container's behalf, and only passes it back if it's on the allow list again. It's pretty magic how if you have full control over what the container can see, you can stop it from doing certain things. Now, we have to do the same kind of thing for proxy authentication, and we once again allow the guest's LSA service to make requests over RPC as if it was the actual host over, and pass that RPC call pretty much exactly the same way you would as a user mode application in the guest over to the original LSA on your host. Fortunately, that's where our second bug comes in. We assume compromise on the edge container, the edge process, and of course, we'd have to also assume some sort of kernel compromise to break out of the sandbox, in which case an attacker can have control over this RPC endpoint talking to the host. It turns out that this RPC call that we were reviewing, and there's only maybe a handful, this one has a handle that we are passing verbatim into the user mode library calling LSA. Interesting thing about this handle is that it's simply a bunch of pointers. And these pointers are now controlled directly by the attacker. And wouldn't you know it, the user mode library actually allows you, actually dereferences those pointers and makes a function call, allowing for a full pointer hijack of the host process that is providing this proxying service. Now this actually brings us to the Windows Red Team's exploit of application guard, which leveraged this feature to accomplish their task. Let me start the video.
You forgot air quotes around feature. But I meant
Feature.
I thought you meant the RPC bug as a feature. That wasn't intended.
And there you are. It's the RPC call itself gives you full code access as the user in medium integrity in your user session. As you can see, HVSI Manager is now running command prompt, which is very exciting. Now, sorry about that. From this situation, we've learned a couple things, and one of them was to kind of review not just the endpoint that we've opened up, but also the constituent components that we were talking to. So a lot of this is old legacy, or maybe not even legacy, but user mode to user mode code, or medium to a system level code. And there are some assumptions that the reviewers and the developers of these tools made that are no longer true because the trust boundary goes beyond simply an user mode application making a call. It's now a user mode application making a call on behalf of a virtual machine. And for that reason, we actually took two steps. And one of the major ones was to split this RPC functionality from that medium IL user mode application that's called HVSI Manager into its own RPC process. This process was then placed in a low privilege app container, and also all the possible mitigations we could throw at it were applied to make even a code execution bug in this space, like the one you just saw, much harder to exploit. And it would make even because this RPC system did not need Win32k at all, it allowed us to block all of that kernel attack surface. So the attacker who had just popped Edge inside the container using a sandbox escape against the Win32k kernel interface would not be able to reuse that once he got out of the virtualized environment and into this app container process.
Another way to say that is, in order to break containment, you'd have to have a Edge remote code execution 0-day, a way to elevate out of the inside app container isolation sandbox, cross the hypervisor boundary with another bug, and then you'd be right back in another app container with Win32k blocked. So what we've tried to do, back to that initial strategy, is make breaking containment as difficult as possible, and hopefully inception for attackers where you just move from one sandbox into another, but keeping containment.
Yep. And let's move on to interaction, aka how does this orange window of magic end up on my screen? So when you launch Windows Defender Application Guard, either explicitly by launching it in Edge or by calling or clicking on the link that is untrusted, the container runs, boots up Windows, gets to the point where it launches Edge with the target address, and displays it on its own desktop, a desktop you can't see. So anyone that's used Hyper-V knows about enhanced session mode, possibly, a little button that allows you to get even better performance and graphics out of your VM. We leveraged that interface to pipe the RDP connection, instead of through a TCP socket connection, UDP socket connection, through VM bus, again, to us, a new Barcelona purpose-built version of Remote Desktop Client that we use to display Edge on your screen. Just Edge, not the rest of it. And we had to work with the RDP team to limit a lot of the sub-channels that we allow over RDP to make sure that we have provided the smallest attack surface for an attacker to use for this scenario. We don't want to allow them to use a lot of the codecs that we allow over RDP traditionally, as in most cases, the trust model is more that we trust the server and not the client, not the other way around. And in fact, this assumption that was built around, that RDP was built with, actually fell us into an interesting bug. So one of the things we did with these restrictions was restrict clipboard types. So instead of passing a lot of these different types, we actually make a call and pass a configuration during connection that says, don't give me a variety of clipboard data. Essentially, just give me text and images over the clipboard interface. And that's more of a attack surface reduction design. But it turns out that there is no code in the client that actually ensures that this exclusion policy is enforced. And in fact, if the server is compromised in the guest, it's more than welcome to send anything it wants, and we will gladly accept it and display it as we would otherwise. So we fixed that, and we changed we reviewed RDP with the assumption that the server was bad for the first time. And then on top of that, we fuzzed it. Again, this time we built a RDP server that's spec-informed and generational fuzzer that, again, targets memory corruption vulnerabilities. And it's been highly successful in finding and securing RDP, not just for our scenario, which is Defender Application Guard, but also for anyone else that has this kind of hostile server risk, so detonation chambers, et cetera. So we've raised the bar for everyone. Moreover, once again, we're more than aware of this. The success of this fuzzer meant that there are enough memory corruption vulnerabilities here that we wanted to make sure that we've given the attackers the worst possible execution space for continuing their attack on us. To that end, we also forked out the RDP client out of the HVSI manager running in medium IL and placed it in another low-privilege app container with as many of the mitigations that we could throw at it while continuing to run correctly and continue to draw the application guard edge window on your screen. And finally, we have a quick bug about settings mirroring, which is the action of actually taking the settings that you have in Edge today. Maybe you're a fan of the dark mode as I am in Edge. It's the best way. And and Edge has to kind of conform in the guest to have those settings, even though we don't pass any of those settings in. Again, our base image is created by just completely user-agnostic data. So the settings mirroring app or process is actually the manager process, once again in Medium. But it can be any Medium application that makes a COM call that says, my client ID is this, insert string here. Please run the necessary XML file that will give you the description of what we need to do. And then pass that information over to the settings worker process inside the guest. Well, it turns out there was a path traversal bug here. And a malicious medium IL application could make a COM call to the container service and say, hi, my name is ... And with this path traversal issue, we could have the container service open any XML file that we could control. That XML file could target a bad DLL that we controlled, and that DLL would be loaded into system integrity on the host. So while this isn't a guest-to-host attack, it was an interesting kind of segue into how we can build systems that inadvertently can affect the totality of the Windows security model. Forgot about this cool explosion. Now, back to Weston.
So we've showed you a bunch of cool technology today and all the underpinnings that have gone through what I'd say is a whole new era of execution isolation in Windows. This is really a key strategy and something we're basing on. So I think what you should expect to see is we'll continue to improve the fundamental capabilities here. Better, faster, stronger VMs that are capable of being extended to essentially any application or application scenario, increasing density and lowering hardware requirements. That's going to enable virtualization isolation technology to reach many more scenarios. And we also want to make it simpler for developers to take advantage of this long term, and also consumers. So This is a very big part of our future strategy, and as you can see, a lot of effort went into not only optimizing the technology, but making sure it's secure. And I guess our ask of the folks here today is we invite you to participate in helping make this secure. Application Guard has a specific bounty that's tied to the Windows Insider Preview bounty. So we've got the general Windows Insider Preview bounty, which has some awesome payouts, and 3 different specific scenarios in which we ask you to report issues. That is Hyper-V, which offers up to $250,000 bounty. There's Microsoft Edge, and then there's Windows Defender Application Guard. So we invite you to participate in that and take a look at the blog link below if you're interested. Thank you very much. Appreciate it. Woo.
So we do have a few minutes before our next session, before we have to kick these 2 gentlemen off stage. As David pointed out, security is not a spectator sport, so participation is sort of incumbent on being part of the tribe, part of the community. I would say, in addition to things on today's show that have fascinated you, you should reach out. If things that you're seeing today frustrate you, we're also pretty good at handling that. We've got broad shoulders here in Microsoft Security, so come to us with what you're thinking. Speaking of what you're thinking, questions from the audience? And we do have microphone runners so that everybody actually gets to hear the question, not just the answer.
So what happens if you're using a older legacy 32-bit application that's going through syswow 64?
Well, sorry?
If the application is going through syswow 64, can it still take advantage of the containerization you talked about?
Yeah, because the guest kernel can, or the guest translation layer can convert that to x64. That can cross the boundary.
Yeah, it still has, it's still a virtualized x64 operating system, and we actually do put syswow 64 into the base
Since WoW is pure software, it's not an issue.
So you talked about the memory tax. What's the CPU tax overhead for running one of these?
That ranges, honestly, depends on the CPU model, but it is fairly moderate. I don't have an overall aggregate benchmark number that I can share for you, but it is in the single percentiles for most cases. A lot of that depends on whether you're playing video and using software rasterization for things like video, but long term, as we accelerate with like hardware GPU that we expose safely, those CPU requirements will go down, but today they're scenario dependent.
Yeah, it's mostly I/O bound, not CPU.
What does logging look like? Anything different, or do things show up in the event log?
For logging in the released version today, we have the ability to log to a VHD that can be mounted in the image and write the event logs off there. Shortly, we'll be introducing the ability to just integrate WEF or Windows Event Forwarding, if you're familiar with that, and that will give you the ability to collect information. But actually, I would say the premier experience for logging and investigation inside of one of these containers is Windows Defender ATP. We've actually integrated the ATP agent into the VM, and so it has full visibility and a bunch of specific detections that are tailored to the code integrity environment of Application Guard.
Okay, so I'd like to ask about the memory management inside the guest. Does it see like all the memory in the host? Like, does the VM see all the physical memory on the host?
No,
none of it.
None of it. It is the GPA, the guest physical address that is assigned to the VM is only the areas that we have virtual alloced inside a specific process called vmm.exe. It's a simple process with no threads. And any direct mapped files are mapped into the VSMB, which is the VM worker process, and that's also VA backed directly to the, a GPA backed directly to the guest, and that's all we give.
Question.
Do we have any comparison of this micro virtualization to products like Bromium?
Comparison in what sense?
They would claim to do similar things and have for the past 4 or 5 years?
I think they're pretty similar in that sense. I would say if there were one advantage, and Bromium's certainly an excellent product, if there were one advantage, it's the deep integration with Windows and our ability over time to drive this down because we own kind of this full vertical stack. Oh, I got to.
Looks like we have a couple more questions, and then I think we'll be wrapping it up. So time for 2 more quick ones.
Speaking of Bromium, have you compared benchmarks between this and Bromium?
We have some performance data. They're very comparable. Again, there are so many different scenarios, hard for me to give you an aggregate metric.
Someone already mentioned logging. How is this from like a forensics perspective, from history stored, et cetera, when a user is using this session versus normal?
So today, in order for you to do forensics, you'd have to go while the VM is still running and run a script to mount a VHD and grab it. In the next version, which actually I think is in Windows Side or preview today, but don't quote me on that, we support WEF. So as long as you're consistently streaming those logs, you'll get at least forensic data in terms of logging. Memory acquisition or other things might be difficult. This is very similar to like ephemeral VMs and the cloud problem. Again, I say Defender ATP is our solution there, which gives you basically a flight data recorder of everything that's happened there. And if they do adopt memory forensics over time, you would have that capability there. But if you can get to the machine, you can dump memory from the VM.
And last question in the back, please.
Yeah, I have a question about the boot time. I know that you have made it like a very quick launch VMs, but you still manufacture the VPs, and you still have to, even if it's a VA-backed VM, you still have to boot it up.
Yep.
Go through the cycle. Have you done anything like this is the state where my VP is, and that's where I'm going to start the edge, or do you actually boot it?
I would say, watch the Windows Insider preview builds. Yep. Absolutely, you're dead on in that there are a bunch of tricks and optimizations for pre-booting or pre-launching for these very specific scenarios. In the version that we released doesn't have all those tricks, but one of the things we're focusing on now is these sort of low-hanging fruit around pre-launching and other things like that. So we'll have more to say on that in the future, but if you watch the builds, I think you'll actually see we'll release some blog with some technical details on what we're doing.
I have a follow-up question.
Sure.
So if it were to become available, is it going to be only for Krypton kind of things, or such a hypercall interface will be exposed to other VMs as well?
What do you mean hypercall interface?
Like this application, this virtual processor is booted to this particular state.
I think Hyper-V containers.
Hyper-V containers already support this. So server-based Hyper-V containers already have I think they call it they call it Zygote, which is a weird name and I don't like it. But essentially the idea is that they start a container all the way until it runs the Windows Server container workload, and they pause it, and then they clone that. Both the VM worker process and the hypervisor VP information to start immediately there and then pass on the guest stuff. Now, the difference with Krypton, as opposed to Xenon, which is Windows Server containers, is the actual number of files that are being direct mapped, et cetera, and also, obviously, much later in the phase of boot that we'd have to hold on to it before launching Edge. So watch that space. You'll see a lot of that coming in. But none of that has any kind of like hypercall from the guest. That's entirely managed by the host side.
Yeah, I meant the host side only.
Cool.
Thank you.
No worries.
Thank you, everybody. Big thanks to Dave and to Sarhan for their time.